The corrections will be like, for example, behind the decimal. So the numbers are not finishing. So here we will now compare the like terms, like the like orders we will compare. And let's first we consider the zeroth order. Now what is the zeroth order here? H0 psi n0 is equal to En0 psi n0. This is the time-independent Schrödinger wave equation. We have solved this equation for many geometries, and this means making no new contribution to the system. So this one is already done. The zeroth order we have already done. So come to the first order. Now first order is the very first term, H0 here, psi n1 plus h1 psi n0, h prime psi n0, and we don't have any first order here anymore, and then this is equal to, this is zeroth order, this is first order, En0 and psi n1, and this one is also first order, plus En1 and psi n0. This is our first order, right? And I can write the second order equation as well. The second order is this term, which is H0 psi n2 plus h1 psi n1, h prime psi n1, and then this is third order, so I will not count this one, is equal. Any second order in this line? Yes, En0 psi n2 plus En1 psi n1, En1 psi n1, and here this term plus En2 psi n0. And this is our second order, the perturbation, the second order perturbation, first order, zeroth order. The zeroth order we have already solved. Similarly, we can have the third order, the fourth, and so on. Clear? So now we will just go one by one. What is our job? Our job is to find out this value, the correction to the wave function, and to find out this value. We will also find the second order correction to the energy, and this, the second order correction to the wave function, you will do this thing by solving a problem in the exercise. So we will, in this lecture, we will first find out this one. It is comparatively easy, while this one we will find it is slightly tough mathematics, but we will do it. And then this one is again easy to find it out. This one you will solve in a problem. So I will go step by step. Whatever the situation is, you will have to go step by step, and then you will be able to solve this thing. We can now start with the first order equation. So H0, let me write the first order, H0 psi n1 plus h prime psi n0 plus h prime psi n0 is equal to En0 psi n1, En0 psi n1 plus En1 psi n0, En1 psi n0. Now our job here in this one is to find out this one, En1 here. We are having En0 here. En0 we already know. Let's say, for example, the En0 for the hydrogen atom. the ionization potential 13.6 electron volt. We know this thing, but we want to find out this thing. Here we will not take example like it may be for infinite square well, maybe for some potential, maybe for Dirac potential. We will later on solve examples on this one, but first we will just find this value, that how much this value comes out in terms of the wave functions. So now you remember that how to get rid of the wave functions. You know that in order to find the magnitude here or the coefficient here, you will have to multiply it with the another wave function. Is these wave functions are orthonormal set of functions. So we will utilize the tactics, and let's multiply this thing, multiplying by psi. I'm interested in psi n, en1 here. So I multiply it with psi n0 and the conjugate of it. If I do multiply with this one, then it will make 1 over here, because psi n mod square and they are orthonormal, so it will make this thing 1 and I will get E n 1 here. So keeping in mind this thing that I want E n 1, I will multiply with this one, and I can write that this will be psi n0, psi n0, because you know in bracket notation I can write this is equal to this. It's when I will take it out of the bracket notation, then it will be psi n0 conjugate, and then it will be applied on this one. So h0 psi n1 plus psi n0 and h prime psi n0. This is equal to psi n0 on en psi n1, while en is 0 here, plus psi n0 and en1 and psi n0 here. I can write this one in that form, because if I want to write something like this, then in integral form it is from minus infinity to plus infinity, psi n0 conjugate, then h0 and psi n1, and then it depends whether I'm integrating a one-dimensional wave function or a three-dimensional wave function. So it then depends. So I can write d cube r here. This you know that the bracket notation we have already discussed them. So now you do multiply them. Okay, one thing here, you can make a vertical sign here as well, like h0 in the middle and then this one, but that makes no difference, so I'm just omitting it, not to write it. Now you know about the h0, that h0 is a Hermitian operator, and for the Hermitian operator you know the condition that if you take its complex conjugate, then it will come out to be the same. It's a Hermitian operator. Hermitian operator, you take the transpose and you take the conjugate and it comes out to be the same. It's a Hermitian operator. So it doesn't matter if I write it here, because when I move it from the kit to the bra here, then it will become conjugate, and as its conjugate is the same, so it will remain the same, and I can write that h0 psi n0 and psi n1. This thing is the same as this one for any operator if that operator is Hermitian operator. Plus, look here, that I don't know about this one, that whether this h prime is also Hermitian or not, because h prime is a perturbation, and Of course, I know that it will be Hermitian because it is H0 and H prime. It will be Hermitian operator, but I don't know its value. What is its value? Like here, it's a small perturbation here, but of what kind of magnitude? Here I know that this is some V naught. So H prime is V naught here in the half. Or if I raise it in the total, then H prime is total V naught in this potential. So I will have to write it is like this one, H prime psi n 0, and then here I can write this psi e and 1 here because it's just a value, and then I can write psi n 0 and psi n 1 plus e n 1 and psi n 0 psi n 0. Now we know about the delta Mn situation. Psi m0 and psi n0 is equal to delta Mn. If m is this is the Kronecker delta. If m is this is equal to 1, if m is equal to n, and this is equal to 0 if m is not equal to n. We know this thing. So we will apply now here on this one. What about this one? H0 on psi n0 is giving you En0 psi n0. So I can write this En0 here and then psi n0 here and psi n1 here. Plus this I will have to put or keep it as like this one because I don't know the value of H prime. If I come here, then this is En1. Okay, this is En0, not En1. This is En0. And what about this one? Here, psi n is 0 and psi n 1. So what about this one? It will become, or let's keep it like this, because I don't know psi n, I don't know about this one, so I will keep it as it is, but I know about this one. And this is psi n0 and psi n0. Exactly that situation in which m is equal to n. So this will come out to be equal to 1. So this is En1 and this value is 1. Now if I look here to this equation, this term and this term are exactly the same. So they are cancelling. This one is cancelled with this one. And now I am left only with En1 on this side and psi n0 H prime psi n0. So En1 is equal to psi n0 H prime psi n0. And this is the first order correction to the energy. This is the first order correction to the energy we have found. Look here. If I apply the perturbation which is here, the addition term to the unperturbed, on the unperturbed wave function, then it will give the first order correction to the energy. And I can now solve an example on this one, and then you will come to know what does this mean. Let's say I am considering again the infinite square wave, and let's say this is a one-dimensional, this is an example, and in infinite square wave I am considering, and here in this infinite square wave, this is x-axis And the width of it is, we have already done this one, the infinite square well of width A, and this is V of X, and I'm having V equals 0 here. Means the potential inside this was 0, while the potential on the wall was infinite. You remember this one. What was our wave function? Psi n0, the unperturbed wave function, was 2 over a sine n pi x over a. This was the unperturbed wave function. And now I consider a perturbation in this one. And the perturbation is such that I just rise it by magnitude V naught. V naught is this magnitude. Now the potential inside here is 0. Okay, this is the same infinite square well. The potential here is 0. Okay, one thing that I did here, this is the potential is 0 inside here, but not in this region. You have lifted it up. So make this correction that here the potential is 0. Here the potential is non-zero in this height. So we have raised it by V naught. So V means the wave function here is this one. But as we have raised the potential by V naught, then H prime is actually equal to V naught here. Because this is the perturbation we have produced in our infinite square well. So come to this one and now apply the first order correction to the energy. En1 means what will be the situation? The energy means the zeroth order wave function will be this one. So here En1 from this equation will be equal to psi n0, and H prime is now equal to V naught, and then psi n0. Psi n0 is actually this value, the unperturbed wave function. Now this is the first order correction to the energy, and as V naught here is not a derivative operator, so I can write En1 V naught and psi n0, and this is psi n0. And I know this thing from that relation that this is equal to 1 is they are orthonormal. So En1 come out to be V naught. And now our problem has finished here, because now the energy of this system will be En0, the unperturbed solution for the energy which we have derived earlier, and plus V naught means this energy plus En1 plus En2 plus En3 and so on. But our problem finishes at the first order correction. There is no second order correction here. So our result will be just approximately here. And then En is equal to En0 plus V naught. And this will give you the first order correction to the energy, and now the energies will be modified like this. You will write that result which you have already written for the infinite square well energy plus this correction term. And similarly, if you do rise this one, let's say this is length A, and at A by 2 you have raised this by V naught. Now in this situation, what your means another example, now the situation is that H prime is equal, you have raised it by V naught in the region V naught in the region when x is between 0 and a over 2, and this is equal to 0, the potential is 0 when x is between a over 2 means greater than a by 2 and less than a. When it is in this situation, you are having 0. When it is in this situation, you have, let me write this thing here like this, that you have raised till here and then it is like this. Up to a by 2, you have raised it by v naught. And then after a by 2, you are with the usual 0 potential here. So here, this is the situation, and now you are supposed to find out the first order correction to the energy. So what En1 will be equal to? It will be equal psi n0 and h prime psi n0. And put the value of this one. So what it will be? If I do put the value of h prime, now h prime is v naught by 2. Whether it's v naught by 2 or not, I don't know. H prime is equal to v naught in this region. And now I don't know to fix it here, like I just write v naught here. And for this, now what I will do, I will just follow the integration.